Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. In the last lecture, we started with the discussion of the fabrication techniques for metal forms, and in this lecture, we will further continue with the same topic of processing of metal forms. So, the main topics that discussed in the last lecture were processing of metal forms in general, and then we discussed in detail about two metal form fabrication techniques. The first one was forming by gas injection and the second one was forming by decomposition of blowing agents. In this lecture, we will discuss in detail about two further forming techniques for fabricating metal forms. The first one is forming by release of dissolved gases, and the second process will be using space holders for metal form fabrication. The main keywords for today's lecture are metal forms, dissolved gases, Sievert's law, lotus metal, space holders, thermal treatment, porous metallic network and lost carbonate sintering process or LCS route. To start with, the first process to be discussed today, that is by forming by release of dissolved gases. So, this process actually depends upon the solubility of a gas in a molten metal as a function of both temperature and pressure. So, solubility of many gases in metals, for example, hydrogen, nitrogen, argon, etc., actually depend upon both temperature and pressure. As is being shown in this plot over here, which shows the solubility of hydrogen in various metals over temperature, we can see that these curves typically show two different regions separated by one abrupt drop or change in slope. So, basically what we can see, if we take for example, the case of aluminum as a model for our discussion. As we know, aluminum has a melting point of 660 degrees Celsius, which is round about here. That means, as you can see, if the temperature of the melt is above the melting point, that means aluminum is in the molten condition, and at that condition the solubility of hydrogen in aluminum is relatively high, which is being shown by this curve over here, and it decreases with decreasing temperature. But suddenly at the melting point there is a sharp drop occurring, and the solubility of hydrogen in aluminum actually drops by more than an order of magnitude at the melting point, and then as we lower the temperature even below 660 degrees Celsius, further decrease in solubility of hydrogen occurs in aluminum. And similar kind of plot actually is observed for other common metals like magnesium, for example, over here, or nickel over here. Also, copper is a very special case, because this phenomena has been used extensively for fabricating lotus copper or gazzer metals, which will be discussed in the next slides. We can also see over here there is a special case in case of iron. So, as we know, iron has several or multiple allotropes, like we know, like delta iron or gamma iron or alpha iron, and that is why we can see over here for the plot of iron there are multiple of those discontinuities at the respective temperatures. So, first we see at the melting point of iron, and then at the point where pure iron or pure delta iron converts to gamma iron, and then at a lower temperature which corresponds to this point where the conversion of gamma or transformation of gamma to alpha actually takes place. So, the basic idea of this plot is that the solubility of diatomic gases or many gases in metals depend upon the temperature, and as we reduce the temperature, as one converts molten metal to solid metal, there is actually a strong drop in the solubility. So, all these phenomena that we see over here this was actually performed at atmospheric pressure of 1 atmosphere. That means, in this slide we see the influence of temperature at a constant pressure over the solubility of gases in molten metal. Now, the opposite phenomena, that means what happens when we maintain the temperature constant and change the pressure, and for that the Sievert's law is applicable. This says that at any temperature the solubility of a diatomic gas actually changes with the square root of its pressure. That means, if we combine both these ideas, that means we at a constant pressure and at a constant pressure for different temperatures and at a constant temperature for different pressures. That means, we can actually vary the solubility of a gas in a molten metal by varying both the temperature and pressure, and these actually gives us the chance to actually fabricate metal forms by varying the gas solubility. So, that means, if we have a molten metal and then this molten metal is actually saturated with gas, some kind of gas dissolved in it, and then if the molten metal is solidified under a low pressure, that will actually cause the ejection of the gas, and then if this gas can be maintained within the molten metal or solidified molten metal, then that may actually give rise to a foam structure, and this is the basic idea which is being followed for this kind of foam fabrication processes. So, the basic structure that we can obtain from this kind of thing, there can be different kind of structures, but also this is a very the schematic of this lotus metal or geyser formation is being shown over here. So, as you can see, this schematic actually explains how these lotus metals are actually fabricated. So, as you can see, first we take actually a crucible, and at this crucible in this there will be dissolved gas in the crucible, and because the molten metal in the crucible is at a high temperature, the solubility of the gas here is higher, and then suddenly this is put under a container or a vessel whose bottom is actually cooled. That means, the bottom of it is a chilled bottom, and the idea is that when this molten metal with dissolved gas is poured on top of this vessel with a bottom chilled container, then there will be solidification along the direction of heat removal, that means along the vertical direction, and then because we are reducing both the temperature and pressure, that will actually reduce the gas solubility, and the dissolved gas will try to eject out, and then if those gases can be entrapped into the solidifying metal, then one obtains this kind of a structure which looks like a lotus metal. That means, as we know, the lotus flowers typically have kind of a very tall stem, and then we can see these elongated pores which looks like the stem of a lotus flower, and that is why these kind of metal structures or these kind of structures are commonly also known as lotus metal or GASAR, gazar. So, this kind of structure is easily formed by varying the solubility of the gas inside the molten metal as a function of both reducing pressure and temperature. So, many metals can actually be fabricated following this, as I just mentioned previously, that as you can see over here. So, almost all metals, they actually follow this kind of a phenomena, and that is why several metals can actually be formed following this fabrication technique. But again, the pore structure, that means this elongated pores, and how elongated, whether the pore diameter is small or large, those factors actually depend upon several issues. So, as you can see over here, two different phenomena can be obtained. For example, as is being shown in the left hand side, the pore structure can be very uniform. That means, that is what we actually want to have. That means, the pore structure is very uniform from bottom to top, and in some other cases we can actually, I mean we do not obtain such uniform pore structure, and in those cases the pore structure actually becomes kind of, it broadens, the pore diameter actually becomes larger as one moves from bottom to top of the vessel. Now, how this is controlled, whether we obtain a uniform and small kind of a narrow pore structure or kind of a non-uniform or kind of continuously increasing pore structure, that actually mainly depends upon the thermal conductivity of the metal. So, as we know that pure metals like copper, magnesium, aluminum, they have a high thermal conductivity, whereas alloys like stainless steel, they have a low thermal conductivity. Now, as I already mentioned, the basic idea for this porous or this lotus metal fabrication is that we need to have a bottom with a chilled bottom with a lower temperature. That means, when the molten metal is poured onto this chilled bottom, then heat will be extracted along the vertical direction, and that will actually lead to the formation of these elongated pores of a narrow diameter or narrow diameter distribution. Now, if the thermal conductivity of the metal is high, that will mean that there will be temperature equilibrium throughout the thickness or throughout the height of the melt pretty easily, and that will actually lead to this uniform and thin distribution. However, if the thermal conductivity of the metal is low, that will actually mean that it will take more time for the temperature to equilibrate over the complete height of the melt, and that will mean that as one moves from bottom to top, that means the temperature gradient will decrease, and that will actually give rise to more broad, that means more or larger pore size. That means, to repeat once again, pure metals like copper, magnesium or aluminum, we can easily obtain from this technique very uniformly distributed elongated pores having very narrow pore size distribution or pore diameter distribution, whereas if we are using some alloys with a low conductivity, it is very difficult to obtain such nice uniform pore structure. Rather, we obtain some kind of a very, it is an inhomogeneous or non-homogeneous pore structure, where the pore diameter actually becomes larger as one moves from top to bottom, from bottom to top. Now, another important variant can be used for this technique to fabricate these gauger metals, that is, we can actually, rather than introducing the gas from an external source, one can also actually introduce the gas directly by foaming inside the metal. So, the basic idea for this is being shown in this slide. So, as you can see, so two different variants are being shown over here. So, in the left hand side, as you can see, again this chilled bottom plate is there. That means, again we are actually making the melt to solidify along the vertical direction. But in this case, as you can see over here, there are these small pellets are there, and these pellets are typically of a gas evolving material like titanium hydride. So, for example, titanium hydride or zirconium hydride, but very often titanium hydride is used. It is a very common metal, it is a very common chemical compound for foaming metals, and it has a low decomposition temperature around 400 degrees Celsius. So, the idea is that in the case A, we have a chilled bottom with this titanium dihydride pellets being placed over there, and then the molten metal is poured directly on these tablets, and then this titanium dihydride, it will decompose and give rise to hydrogen gas, and this hydrogen, it tries to kind of eject or kind of release from the melt, and it actually gives rise to this elongated pores along the vertical direction. In another variant of this process, as is being shown on the right hand side, again the same chilled bottom is used, but instead of putting these titanium hydride pellets inside this chilled bottom, we put these pellets in the crucible which contains the molten metal. That means, the hydrogen gas is evolving directly inside the melt, and then when this melt is poured onto this container with the chilled bottom, then again these gas bubbles, they will have an elongated shape along the vertical direction, and that will again give rise to this Gazer metals or lotus metal structure with very elongated pores. So, typical microstructure. So, as you can see over here, this slide actually shows from a research article, we show here different tomographic images of these porous metals at different orientations, and as you know, tomography is a very powerful technique to find out the internal structure of any material if the materials have very large density difference. And as you can see over here, along different angular orientations, we can see these very elongated and very uniformly distributed these elongated pores, which have been fabricated by using this technique. And these images actually correspond to lotus type porous copper. So, porous copper has been very often fabricated using this technique to fabricate this lotus metal kind of structure. So, after this, the next technique that we will discuss is metal foam fabrication using space holders. So, until now, whatever techniques we mainly discussed, they involve some gas ejection. Now, space holders are actually sacrificial materials. So, we discussed about the space holders when we discussed about the ceramic foam fabrication or porous ceramic fabrication, and a similar concept is also used for fabricating metal foams using space holders. And again, different kinds of space holders can be utilized, as we discussed for porous ceramic fabrication. We can use components or compounds like potassium carbonate, sodium chloride, some kind of wax, and also some other components can also be used for metal foam fabrication. Now, what is the basic concept or philosophy for fabricating metal foams using this technique? So, this is actually explained in this schematic diagram, as you can see over here. So, in this case, again the starting part or the starting materials are some space holder particles, as you can see over here, and some metal powders. Now, the main thing is that in this particular case, for fabricating porous metal using this technique, the size and dimensions and shapes of the space holding particles are extremely important, because the final pore size, pore morphology, and pore dimensions and pore shape, they actually completely depend upon the space holder particles. This is actually one big advantage of using the space holder technique, because we can actually control the pore size and pore distribution and the pore and the amount of porosity very precisely. Because the previous techniques, whenever we use this dissolved gas, the pore size we had very less control, and it was actually just simply controlled by the amount of gas that is evolving and its distribution. Whereas in this case, because we are actually using the space holders and we have control over the amount of the space holders and their size and their distribution, so we can actually have whatever pore size distribution or whatever porosity as per our will. So, what is the basic process once again? So, that means we again start with the same the space holder particles, depending upon how much amount of porosity we use and what is the pore size we use, and some metal powders, and then these space holders and the metal powders, they are mixed intimately. That means we use some kind of a tumbler mixer or some kind of mixer where these space holders and metal powders are intimately mixed. One important point at this stage is that the density of the space holder particles and the metal powders should not vary, should not differ a lot, because if the density is very much different, that might actually lead to non-uniform distribution. But if that stage is kind of taken care of, then we obtain this mixture, and then this mixture actually undergoes the first stage of preliminary fabrication. That means the green body is fabricated. We already discussed about this green body fabrication in the previous lectures when we discussed about porous ceramic fabrication. So, again the same technique is used over here. So, we can use either cold isostatic pressing or uniaxial pressing. So, we obtain a green body, and then there can be two different ways. After this green body, that means after this green body fabrication, we can either remove the space holder directly at this stage and then undergo sintering, or it is vice versa. That means we first undergo sintering, do sintering, and during the sintering process there is neck formation between the individual metal particles, and they actually form a very nice solid structure, and then wherever we had the porous bodies or the porosities, those regions actually either, if it is a polymer pore former, then they will kind of pyrolyze during the fabrication process, or if it is some kind of a salt like sodium chloride or potassium carbonate, then after this whole structure is kind of fabricated, we can actually dissolve the thing by this salt by leaching That means once the porous metal has been fabricated with these salt particles inside them, because typically the salt particles, if you are using aluminum for example, the salt particles have a higher melting point. That means the salt particles will remain inside the porous body, and then the whole foam structure could be actually put in water, and then the salt will be leached out, and this way we actually obtain a porous metal by this technique. And in the other variant, as I just mentioned, we can also try to first remove the these pore formers by some kind of sacrificial process like some pyrolysis or whatever, and then this thing is put under sintering, so that the metallic regions between the individual pores, they get bonded together, and we obtain a very nice porous structure with uniform pore size distribution. So, one variant of the process was actually used in our group to fabricate porous copper samples. So, as is being shown in this slide over here, and this process again had 4 different stages. So, as you can see over here, these stages are being shown over here. So, initially we used copper powder because we wanted to fabricate porous copper, and then we used potassium carbonate as the pore former. I mean, we have also used in the future, we have also used a mixture of potassium carbonate and sodium chloride, because these both are kind of salt particles which can be leached out and give porous morphologies. But in this case we used only copper and potassium carbonate, and the amount of KTCO3 particles were varied to obtain a porosity over a wide range of 30 to 70%. So, then these particles were intimately mixed in a tumbler mixture, and then we obtained a green body, and then after this green body, after compaction, it was put under sintering at 950 degrees Celsius, and then this green body, this sintered body was put under water for 24 hours to leach out the potassium carbonate, and this way we obtain the porous body as is being shown schematically in this image over here. The macroscopic image of these porous copper samples are being shown over here. So, these samples are pretty large. So, that shows actually that this process is actually very versatile, and it can actually give rise to large samples with a wide range of porosity, and typical pore morphology is being shown over here. That means, you can see that this process actually gave us a very nice interconnecting and interpenetrating porosity, where all the pores are kind of distributed throughout the sample, and the amount of open porosity was pretty high. That means, this sample had a large amount of open porosity, and this open porosity actually allowed to leach out the sodium chloride and potassium carbonate as the pore formers very effectively from inside the pores. So, this is a very versatile technique for fabricating such samples. Now, this process which I just discussed so far, this space holder technique, so far I discussed about the powder metallurgy process, where the initial materials were both metal powder and some space holder particles. Now, the similar concept can also be used to actually for liquid metal casting process, where actually the metal is not taken as a powder, rather we take the metal in the form of we melt the metal, and then that is actually used to fabricate the porous body. Now, as we all know that a liquid metallurgy process has some advantages of a powder metallurgy process. One thing is that powder metallurgy process is more expensive, because metal powders are more expensive than bulk metals, and second thing is that the powder metallurgy process, they always has some size limitations, because the processes like pressing, sintering and all those things, they actually are limited in the size capacity. So, for fabricating like if a foam can be fabricated in the melting casting route, then the productivity will always be higher, because in melting casting route even some like large castings can also be fabricated. So, what is the basic concept of fabricating these metal forms using space holder particles following the melting casting route? Again we need some space holders, and again the space holders can be some kind of, again some salt can be used, or it can also be some particles or something else like some preform can be fabricated. So, the basic idea is that we fabricate a porous preform, and then the molten metal will be actually infiltrated inside the porous preform, and then the preform, after the melt solidifies, the space holding preform will be kind of removed, and that way the foam will be obtained. But there are also situations where the pore formers or the space holders, they remain inside the structure. That means we can obtain some kind of, there is some kind of material or porous material called cenosphere. So, these cenospheres are actually those are actually like some kind of ceramic spheres or hollow ceramic spheres, which are commonly obtained from many plants, like many cement plants or many steel plants. These often cause some pollutions, and these can actually also be used as pore formers, because these are microspheres with diameter up to around 500 microns. These are very light materials, and these can be very effectively used as the space holders. But the difference here is that the space holders, these cenospheres, they remain inside the foam after the foam has been fabricated. That means these cenospheres are not leached out or removed during fabrication or after fabrication, they remain inside the foam. But there are other techniques when some salt is being used or something like that, then after the foam has been fabricated, the metal has solidified, this salt has to be leached out to give rise to the porosity. So, a schematic of this process is being shown over here. So, if we see here again, the starting point is some kind of, we have the molten, we have to first fabricate a preform. So, as I just mentioned, here the main thing is that we need a preform or the pore former, which will actually give rise to the porosity. That means, in this case they use some kind of a mixture of salt and flour to get some kind of a preform, and then they actually make these preform balls or the preform spheres are actually created, and then these preform spheres actually undergoing some heat treatment, because this heat treatment process will actually give rise to some kind of stability. That means, if these preforms are not stable enough, then they will not be able to survive the high temperature metal, and they might actually succumb to the molten metal pressure, and that means some kind of heat treatment was applied to give this preform some kind of some rigidity. And after that, once it is made, this thing is put under a container, and then very often we need to apply some vacuum, because there is always some air pressure which actually will oppose the flow of the metal inside in the downward direction. That means, if all the pore channels are filled with air, we need to remove the air before the metal actually can infiltrate the porous preform, and that means very often some vacuum is applied, and after that the molten metal is poured, and very often we also need to apply some kind of gas pressure to actually let the metal flow inside this preform, and then when the thing solidifies, when the metal solidifies, we obtain this solid metal with this preform inside it, and then this preform is leached out, and we obtain a very nice homogeneous and uniform pore structure or porous body with such kind of pore structure as is being shown over here. So, this is again a very versatile technique for fabricating porous metals, and the main advantage of using these space holders is that, as I already mentioned, that we can actually obtain a very nice and homogeneous pore structure. That means, whatever pores, we can have a very strong control over both the porosity and pore morphology. That means, even if we want, for example, different regions with different pore size distribution, for example, a graded porous structure, then again this process can be an ideal process, because we can actually fabricate a green body with different porosity distribution over different regions. So, this is a very versatile process for fabricating porous bodies, but typically in this case we have one limitation, that is the porosity is actually limited to 80%, because if the porosity becomes too high, then again the green body will have a lower amount of strength, and then it is not actually fabricable. That means, it is actually used for up to 80% porosity, but it is a very versatile technique for actually giving rise to many different pore structures and pore morphologies. So, to conclude today's lecture, in this lecture we discussed about two different fabrication techniques for metal foams. The first one was based upon the solubility of gases in metals as a function of both temperature and pressure, and the second technique that we discussed was how to fabricate metal foams using space holders, and we discussed about both the powder metallurgy technique and also the melting casting route. Both actually gave us a very well defined and over a wide range of porosity some very nice quality metal foam structures. So, these are the references which were used for the material discussed in today's lecture, and in the next lecture, which will be the final lecture on metal foam fabrication, we will discuss about 4 more techniques, that means foaming by solid precursors, investment casting which is very similar to replica technique, metallic hollow sphere structures, and fabrication of foam sandwich panels. Thank you very much.